Hi, I'm Harsh Parekh, and I will be presenting to you my work with Babak, Mo, Sudeepa, Ulise, and Dan on causal relational learning. In this work, we developed CaRL, an end-to-end framework for causal inference on relational data. Causal inference is relevant in many settings. For example, healthcare sciences, they study efficacy of drugs. In social sciences, we study the effectiveness of a policy. And in education research, study fairness in admission processes. You have probably heard of correlation is not causation. But what is causation? There are standard approaches for causal inference in statistics and artificial intelligence. Rubin's causal model and Pearl's causal models both concern about computing the effect of intervention. What would be the outcome of interest if we intervene or change another variable? For example, what would be the number of recovered cases if patients take a drug versus they take a placebo? In Pearl's causality, we denote intervention using do operator. Let me walk you through an example. Consider if we want to study the efficacy of a drug in curing disease. The treatment effect of a drug will be the difference in the outcome if patients were given the drug, that is, do drug equal to Y, and if patients were given the placebo, that is, do drug equal to N. These are two possible interventions. A nice way to conceptualize this intervention is to assume there are two additional attributes in the data that measures whether patients are cured in a hypothetical world in which patients take the drug, that is, do drug equal to Y, and in a hypothetical world in which patients do not take the drug, that is, do drug equal to N. Statisticians refer to this as potential outcomes. Causal inference would be very easy if we had potential outcomes. However, for each patient, at least one of the potential outcomes is missing. In this sense, causal inference is a missing data problem. Fortunately, it is possible to measure the missing potential outcome under some assumptions. A principal way to state and verify these assumptions is to use Pearl's causal graph. These are simple DAGs in which nodes represent the attributes and edges represent the causal relationship between them. However, both Pearl and Rubin's causality are based on assumptions that the study consists of a set of similar or homogeneous entities, that is, a set of patients, students, customers, described in a single slide table. Our interest is in causal inference on relational data, and classical causal inference methods are not applicable to relational data. Relational data typically has multiple entities occurring across multiple tables in a many-to-many relationship. And often, in the causal question of interest, the treated entity and the outcome entity might come from different relations. In other words, they might be heterogeneous. For example, if we want to know the effect of prestige of an author on the review score of a paper, prestige is the treatment of the author, while review score is the outcome measured on submission. Further, different papers may have different number of authors and different number of prestigious authors. This data cannot be represented in a single slide table, thus the existing causal frameworks are inadequate for causal inference on relational data. In this work, we introduce CaRL, which is an end-to-end framework for causal inference on relational data. We propose a declarative language based on Datalog for representing expert knowledge about process that generates relational data. We give semantics to complex interventions and causal queries in relational domains. What is the effect of an author's collaborator prestige on his or her submission acceptance rate? We prove sufficient conditions under which complex causal queries can be answered from relational data. And importantly, we do all of this in a declarative manner. Hence, CaRL makes causal inference accessible for non-statisticians. Big picture. CaRL takes in a relational database, background knowledge about potential causal links, and a causal query of interest. transforms the input to a single flat table with homogeneous units, and performs causal estimation. Next, I will explain each step of CaRL's methodology in detail. CaRL assumes a relational database with entities, relationships, and attributes. So for example, author A1 or paper S2 are entities, while authorship A1 S1 is a relationship, and prestige of author A2 is an attribute. Right? In CaRL, it is legal to intervene on attributes. However, the relational skeleton is immutable. That means you can ask, what is the effect of prestige on review score? While asking, what is the effect of A1 authoring paper S1 is not legal. Next, users can input background knowledge in CaRL using Datalog-based relational causal rules. Background knowledge encodes the expert knowledge about potential causal links. So here, if we know that the qualification of an author affects the quality of a paper, then we can express it as rule number 2. This relational causal rules are necessary for causal inference on relational data and are more expressive than first order causal graphs. Lastly, CaRL allows users to ask complex causal queries. Here, we are interested in knowing the effect of prestige on review score. Note that each paper can have arbitrary number of authors, right? Thus, we can ask these causal questions in multiple different ways. We can ask, what is the effect on review score when all the authors on a paper are prestigious? Or we can ask, what is the effect on review score when at least one of the authors on the paper is prestigious? These two are different causal questions, but are of same flavor. And CaRL allows users to ask either of these questions. Next, we will look at CaRL's methodology. As we saw, CaRL takes in a relational database, causal background knowledge, and a causal query of interest. Using the given input, CaRL performs skeleton traversal, where it maps the attribute in causal background knowledge to entities and relationships in relational database. Following the skeleton traversal, CaRL grounds the causal graph to generate grounded causal DAG. We substitute the placeholders for attributes with actual attribute value from skeleton in relational database to generate a grounded causal DAG. Next, we use the causal query and the grounded causal graph to identify outcome variables, treatment variables, and confounders. So here, the review score is the outcome variable, while the prestige of the authors are treatment variables, and as author qualification and paper quality are potential common causes for prestige and review score, they're confounders. Now, we want to generate a single flat table such that each row of that table corresponds to an outcome unit. Here, the outcome unit is a paper submission. And if a paper submission is linked to a treatment variable or confounder by a many-to-many relationship, then we apply a summary function to convert a bag of variable-sized features to a finite-size vector. For example, here, paper S1 has two authors, A1 and A2. Their qualifications can be summarized by using a summary function, let's say average of qualifications of both the authors. This is a simple example of one-dimensional summary functions. However, we can use complex summary functions also. Now that we have homogeneous units in a single flat table, we use causal analysis methods to estimate causal effects. We show the proof of correctness of CaRL methodology in our paper. Please read it for more details. We demonstrate CaRL's end-to-end functionality using experiments on two datasets. First is the paper review data from openreview.net, where we have information about authors and paper submission to both single-blind and double-blind conferences. And second, we have hospital stay data of patients in critical care units, and we are interested in understanding the effect of insurance plans on healthcare outcomes of the patient. We also perform more experiments and showcase the CaRL's performance in paper. We are interested in understanding if in single-blind and double-blind conferences, are the reviewers influenced by authors' prestige? So if we were to look at naive difference of review scores for papers with and without more than 1/3 prestigious authors, then in both single-blind and double-blind venues, we see positive correlation, which is shown by yellow bar. However, once we control for the confounders like the qualification of the authors, we find that while in single-blind conferences, the reviewers might be influenced by author's prestige, in double-blind conference, that is not the case. It is shown by the green bar over here. Thus, double-blind conferences, unlike single-blind conferences, are successful in ensuring that the reviewers are not influenced by the prestige of the authors. On the patient stay dataset, we inquire if for any admitted patient, do health outcomes depend on if they have insurance or not. The blue bar shows outcome for patients without insurance, and the red bar shows outcome for patients with insurance. If we look at naive correlation shown by the yellow bar, we might be tempted to conclude that not having insurance makes the patient worse off. However, once we control for the severity and complications, we find causal effect of insurance is almost negligible. Hence, health outcome of an admitted patient does not depend on their insurance plan. In today's presentation, we introduced CaRL, which is an end-to-end framework for causal inference on relational data. It is equipped with machinery to answer complex causal queries. Also, CaRL is an easy-to-use interface for users with application in academia and industry. Thank you.